Alright, so this set of notes is going to start. So in 7.1, we introduced multivariable functions and how they work. Again, very similar to single variable functions, just you have to be careful of all the different parts. Now we're going to do the calculus of them. Alright, the calculus of multivariable function involves what's called partial derivatives. So remember, a derivative is looking to find the rate of change, the speed, right? How fast, how slow is my function changing? Right, that's the derivative. With multivariable functions, it gets a little trickier. The reason why is we can only take the derivative with respect to one variable at a time, one variable's rate of change. Where that comes from is, remember that the definition of the derivative is the limit as h approaches 0 of the average rate of change. All right, where the average rate of change is divided by an h term, and that h term can only represent one change. All right, h can be either the change in x or the change in y. It can't be both. All right, so there's the right with respect to only one variable. All right, so what we do is we find what are called partial derivatives of multivariable functions. They're called first order partial derivatives because it has to do with the order, and that'll come into play a little bit more when we get to the second order partial derivatives. Now, we're only going to do two variable functions, but the idea would extend to more than two. All right, now since we're only doing two variable functions, there's two variables I can take the derivative with respect to, and so we get two first derivatives, first order partial derivatives. If I had three variables, I'd have three first order partial derivatives. If I had five variables, I'd have five. All right, so see how it would continue on, and we could go as many as we want. All right, but like I said, we're only doing two. All right, so we start with our function. Our variable z is our output, equals our function f of xy. Xy are inputs, and those are the variables that can change. So the first partial derivative we're going to look at is with respect to x. All right, so that means x is the change we're interested in. When x changes, how does the function change? So a function change per change in x, which means we're going to hold y constant. Y is not changing. All right, so y behaves like a constant. All right, and so we treat it like a constant. It's a unknown constant. Again, y is going to represent a y value that's fixed, therefore it's not changing, and it behaves just as if it was a number like the number 10. Alright, so when we take the partial derivative with respect to x, this is called the first order derivative with respect to x. It's denoted by, so I'm going to use the rate of change notation and the function notation. The rate of change notation would be the change in my z, my output, over the change in x. The function notation is f sub x of my f of xy. And the reason why I'm using both notation is because I will most of the time use the function notation, f sub x. That sub x means I'm taking the derivative of x, or the derivative of f, with respect to x. X is what's changing. This is actually showing you that's what we're doing. It's the change in my z, which is my function, per change in the x value. And again, the Connect book will use this notation, so make sure you recognize that's what it's asking for. It's finding the derivative of my function with respect to x. Sometimes I'll also use the function notation, change in my function over the change in x. Alright, so the rate of change notation. Alright, let's do a simple example. Alright, so I want to find the rate at which the function is changing when we change x, and we're holding y constant, therefore it behaves just like a constant. Alright, so the function we're going to look at is, it's just going to start with a simple function, 3x squared minus 5xy plus 4y to the second. Alright, so I'm going to take the derivative of this function with respect to x, or using the function notation f sub x of xy, and I'm going to write it out. I'm taking the derivative of this function with respect to x. Alright, I'm taking the derivative of this part of the function with respect to x. And I'm taking the derivative of this part of the function with respect to x. Right? Remember, the derivative is to take the derivative of each individual piece. That's all I did here with this notation. So this is the derivative of the first piece, the power function, 3x squared with respect to x. This is the derivative of the mixed term, right? X's and y are mixed together with respect to x. And then the last term, 4y squared with respect to x. Remember, y behaves like a constant. Alright, so the derivative of this with respect to x, well, this is an x function, right? So I take the derivative just as if it was just what we did in the last sections, using my power rule. So I'm going to get 6x to the first, alright, so there's the derivative of that piece. Minus, alright, so 5 is a multiplier, and y is a multiplier, alright? So 5, again, the multiplier rule is the constant comes along. Well, 5 is going to come along because it's a constant multiplier. Y is being held constant, so it behaves just like the constant 5. It is also going to come along, alright? So I get 5 times y, and then I take the derivative of the variable part. Well, the variable part's x, right? Take the derivative with respect to x. And so the derivative of x is just 1. Right? We don't usually write that down, but that's what's happening. 5y are the constant multipliers that are coming along. I take the derivative with respect to x, so the derivative of the variable x is just 1. And so there's the derivative of that middle expression. All right, then the last piece, I take the derivative of 4y squared with respect to x. So 4y squared, I want to know how it's changing when x changes. Well, there is no x variable there, right? 4 is constant, y is constant, there is no x, so there's no change in x, and so that just zeroes away, right? If there's no x value, there's no rate of change, right? And so no x value, it zeroes out, and so the derivative of this function with respect to x is 6x minus 5y, and there's the first order derivative of f of xy with respect to x. All right. Similar thing's going to happen then. So there's one of the partial derivatives, the first one. All right, now the second one. All right, so we do the same thing with the y variable. All right, so we have our function z equals f of x, y. Want to take the partial derivative with respect to y. So now y is the change. All right, so if we're writing this as a limit, h would represent the change in y, which means x is being held constant. Right, x is fixed or held constant. So we're taking the first derivative, first order partial derivative of our function with respect to y. Alright, so it's denoted change in z with respect to the change in y. Or again, if we use the function, our f sub y x. And again, what this means is how is our function f of x changing as y changes? What's the slope with respect to y? Alright, is it increasing, decreasing? What is it doing? Alright, and so same thing, but now with respect to the y variable. Alright, so I'm going to look at the same function I had before, but now take its derivative with respect to y, and it should come out different, right? Our function changes differently in terms of y than it does in terms of x. Alright, so the function was 3x squared minus 5xy plus 4y squared. Alright, so I'm going to take the derivative of my function with respect to y. So f, not prime, f sub y of xy. Alright, so again, I'm going to write out the pieces, what we're doing. We're taking the derivative of each piece, each function piece, with respect to y. Alright, so as y changes, how do each of those parts change? Alright, what's the derivative of each of those parts with respect to y? Alright, well the first function is the function 3x squared. How does 3x squared, that function, change as y changes? Well, there is no y part, right? And so it doesn't change. 3 is a constant, x is being held constant. Alright, so there is no change, there's no y part, so that zeroes away. Alright, the next one, again, 5 is a constant, so it comes along, it's a constant multiplier. X is behaving like a constant, right? We're holding x constant, so it behaves just like the 5, so x comes along. It's the y that we're taking the derivative of, right? We're taking the derivative of y with respect to y. Well, the derivative of just y is 1. And again, we don't usually write the 1, but that is what's happening. 5 is constant, x is behaving like a constant, and so since they're constant multipliers, they come along. I take the derivative of y, which is 1. Alright, then the last term, I'm taking the derivative of 4y squared with respect to y, and so it just behaves like the power rule, right? Pull 2 out to get 8, y to the first, and so if I write that simplified, I get negative 5x plus 8y. And so the function's behaving differently in the y direction. Right? It has different rates of change in terms of y than it does in the x direction, right? In the x direction, it's 6 times x minus 5 times y. In the y direction, it's negative 5 times x plus 8 times y, and those are different. Those would give me out different slopes, different rates of change. All right, so we're going to practice a few, right? And then we'll practice some more in the next set of notes. All right, so we're just going to do the first page, and then in the next set of notes, I'll do the second page. So we're going to start off with some simple examples, and then we'll get to more complex one in the next video. All right, so here's my function f of x. I want to take my derivative with respect, so again, I'm taking the derivative of my function with respect to x. And so I'm not going to write out all the pieces that I did last time, but if you want to the first few times, it might be helpful just to remember what's changing and what's being held constant. The rule of thumb is when I'm changing x, I take the derivative of all the x parts, all right? So all of the x's will change. If it doesn't have an x, it'll be a constant. So 3y is a constant, it'll 0 away, there's no x. 12 is a constant, it'll 0 away. And so I just take the derivative of the x parts. And so the first one is 0.3x cubed, and so I use the power rule. It's going to be 0.9x to the second. All right, this was actually the one we did on the previous page. Right? The negative 5 and the y are constant multipliers. They come along. The derivative of x is just 1. All right, and again, I'm going to write it down just to remind you what it is. You don't have to, but I'm just reminding you of what you're doing. I'm taking the derivative of x because that's what I'm doing. Y is a constant, 5 is a constant, and they're coming along because they're constant multipliers. All right, the next term is 2x to the second, which is 4x to the first, and then the next one is negative 5x. The derivative of that with respect to x is 5. There's no x value in 3y, so it zeroes away. No x value in the 12, so it zeroes away. And so there's my first order partial derivative with respect to x. All right, now I do the same thing with respect to y. All right, so again, I look at my function and I only look for the y parts. All right, so the negative 5xy, there's a y part there. And the 3y, there's a y part, and that's it. The first term, 0.3x cubed, no y, so it zeroes out, so there's no change in y. The 2x squared, there's no y, so it zeroes out. The negative 5x, no y, it zeroes out. And 12, no y, it zeroes out. So there's only two terms I have to take a derivative of. The negative 5xy and the positive 3y. All right, so negative 5xy, again, the negative 5 is a constant. The x is a constant. I take the derivative of y, which is 1, which again, you don't have to write that down. I'm just reminding you I did take a derivative, but the derivative of y just happened to be 1. So that would be negative 5x if you wanted to write it simplified. All right, plus the next y term is 3y. The derivative of 3y is just 3. And so there's the derivative with respect to y. All right, the next example. All right, so p sub x, again, the derivative of my p function with respect to x. So I only take the derivative of the x part. So negative 4x squared, no x in the next term. Negative 4xy, negative 1920x, y term, constant term. So that's it. There's 3 parts with x. When I'm taking the derivative of x, those are the only parts that are changing. All of the other parts are held constant, and so they zero away. There's no change. And so I just take the derivative of the negative 4x squared, which is going to give me negative 8x. Again, this is the mixed rule. The mixed rule is the negative 4 and the y come along. And I'm not going to write it down this time. The derivative of x is what we're taking. The derivative of x is 1. All right, so it'd be negative 4y times 1, which is just negative 4y. And then the last term with an x in it is the 1,920 times x. 1,920 is a constant that comes along. The derivative of x is 1. And so there is my first order derivative with respect to x. All right, now with respect to y. Changing my p function with respect to y, p sub y. And so now I only do the y value parts. So I'm going to circle the y values, all right? So no y value here. All right, this has a y value. This has a y value. and this has a y value. So those are the three terms with y values. The other terms have no y values, so there's no change with respect to y, so they're being held constant, and so they'll zero away. So the only parts I take the derivative of are the ones with the y parts. Alright, so first term zeroes out. The first term I take a derivative of is the negative 6y squared, so that's going to be negative 12y minus the derivative of negative 4xy with respect to y, so it's the y part I'm taking the derivative of. The negative 4 and the x are constant, so they're constant multipliers that come along. Derivative of just y is 1. So it'd be negative 4x times 1. I'm leaving off the times 1, because when we multiply by 1, we just get the original expression. Next term zeroes out, no y, and so the last y term is the 1600y. The derivative of 1600y is 1600. Alright, the 80,000 zeroes out. It is a constant, and there's the derivative with respect to y. Alright, so the last one for this set of notes, and we're going to do some more in the next set. They're going to just be slightly more complex. Actually, this one's more complex than those. Those were polynomial examples, which tend to be pretty straightforward. This is a non-polynomial example. Alright, so I might write this a little bigger so I can see it. So 3x to the second times y cubed plus 3 times the natural log of x times y. Alright, so there's more so this is more complex. There's more going on in here since I have this natural log. I have the natural log of x times y, so this is actually going to require my chain rule on this log function. So this will be the first chain rule we'll be doing. Alright, so first the derivative with respect to x. Alright, so the change in my function as x changes. Alright, well both terms, there's only two terms. Alright, both terms have x terms and y terms. So I'll take the derivative of both, right? I've got x terms in both of them, and y terms in both of them. Alright, so the first one is x is changing, and so I'm going to write down my constants first. 3 is a constant, y is being held constant, and so the 3 comes along. The y cubed is behaving like a constant. It's just an unknown constant, and so it behaves just like the 3. It's going to come along. The part we take the derivative of is the x part, because that's what we're taking the derivative with respect to. So 3 is a constant multiplier, it comes along. The y cubed is a constant multiplier, unknown constant. Alright, but it's still a constant that comes along. The function part's the y squared, or sorry, the x squared. Alright, I take the derivative of x squared, which gives me 2x to the first. Alright, so there's the first term, derivative with respect to x. Alright, now the second term with the log, which I will have to use the chain in. 3 is a constant multiplier, it comes along, so 3 times. The derivative of the natural log, using the chain rule, is 1 over the function inside. Well, the function inside is x times y, so it's 1 over x times y, times the derivative of the inside. We're taking the derivative of the inside with respect to x, so x is going to be the derivative, which the derivative of x is 1. Y is a constant multiplier, so y is going to come along, so the derivative of xy with respect to x is y. It'd be y times 1, but we just write y down. And then I'm going to clean that up. Alright, I'm going to rewrite this. I'm going to multiply the 2x times 3 to get 3 times 2, which is 6x, y cubed, plus, and I'm going to rewrite this as a single fraction. Actually, that y will, those y values reduce to 1, or cancel each other out, and so I'm just with 3 divided by x. Alright, there's my first derivative of this function with respect to x. Now do the same thing with respect to y. So f sub y. Alright, so now I look at the y parts. X is my constant. Alright, so y is the function that I'm going to take the derivative of, because I'm taking the derivative with respect to y. 3 is a constant. It comes along. X squared is a constant. It comes along. It's an unknown constant, but it behaves like a constant. I take the derivative of the y part. So I'm taking the derivative of y cubed, so that's going to give me 3y to the second. Alright, done with the first term. Now to the log term. The first part's exactly the same. Alright, the outside function doesn't care if it's x or y, it behaves the same way. It's going to be the constant 3 comes along. Derivative of natural log is 1 over xy. Alright, which again, exactly the same as the previous one. This is where it changes, because now I'm taking the derivative of the inside with respect to y. So it's the y part I'm taking the derivative of. Well, the derivative of just y is 1. X is a constant. All right, so the derivative is simply x. X comes along. And so there is the derivative with respect to y. And then I'll clean it up a little bit. All right, so I'm going to multiply this 3 times that 3 to get 9. X to the second, y to the second. Same thing here. This x value will reduce with that x value. And then I'll rewrite it as a single fraction. 3 divided by y. And there's my derivative with respect to y. All right, and so we're going to stop here. And so on the next set of notes, we'll start into practicing more of them. They're going to just be slightly more complex. We're going to involve some of our other rules. All right, and we'll do that in the next set of notes.